Statistics Week 8, Part 4, Calculating with Confidence Intervals. Here's an example based on what we just did in the last video. Suppose scores on exams in statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean score, of 68. Find a confidence interval estimate for the population mean exam score. That is the mean score of all exams of this type of statistics test. Find a 90% confidence interval for the true population mean of statistics exam scores. To find the confidence interval, you need the sample mean, x bar, and the EBM. Now, we know in this case, we're given that the sample mean is 68. The confidence interval level with sigma equals 3 and n equals 36 is going to be 90%, so CL is 0.90. So we have to follow the steps that we just did in the previous video. Since CL is 0.90, alpha is going to be 0.10, 1 minus 0.90. Alpha over 2 then is half of that, or 0.05. Z of alpha over 2 is Z 0.05. And we already know from previous calculation what this is going to be, but we'll follow through what we did here. The area to the left of Z sub 0.05 is 1 minus 0.05, which is 0.95. And using inverse norm on the calculator, we will get that value that we got before, 1.645, which we can associate with this confidence level, 0.90. So Z of alpha over 2 is 1.645. Our next step is we want to find the error bound for the population mean. That's going to be 1.645, our Z of alpha over 2 score, multiplied by sigma, which is 3, divided by the square root of the sample size, 36. We get 0.8225. Now we're going to write the confidence interval. That's going to be x bar minus EBM, comma x bar plus EBM. So in this case, it's going to be 68 minus our 0.8225, and 68 plus 0.8225. So we get 67.1775, 68.8225. And finally, we would say, we estimate with 90% confidence that the true population mean exam score for all statistics students is between 67.18 and 68.82. Here's another triad exercise you should work through to see if you can get the result for this. You should stop the video now and do this practice. (8.2) Suppose average pizza delivery times are normally distributed with an unknown population mean and a population standard deviation of 6 minutes. A random sample of 28 pizza delivery restaurants is taken and has a sample mean delivery time of 36 minutes. Find a 90% confidence interval estimate for the population mean delivery time. In this case, the result is similar to what we just did in the example. To find the confidence interval, you need a sample mean, x bar. X bar is 36. Our calculation for the confidence level of 90% is the same as what we just did. We get a Z score, Z of alpha over 2 is 1.645. Our error bound measure is 1.645 times 6 over the square root of 28, which is 1.865, giving us a confidence interval of 34.135 to 37.865. You would then interpret that data below. Here's an example. Suppose we change the statistics exam problem above by using a 95% confidence level. We want to find a 95% confidence interval for the true population mean statistics exam score. To find the confidence interval, you need the sample mean, x bar, and the EBM. X bar is 68 again. We're going to find the confidence level with sigma equals 3 and n equals 36, the confidence level being 95%. That's going to give us Z 0.05, our Z alpha over 2 score of 0.975. Using inverse norm with 0.975 gives us 1.96. So z alpha over 2 is 1.96. 1.96 is a value that you can then associate with this 95% confidence level anytime you need to use that. The error bound for the population mean will be 1.96 times 3 over the square root of 36, which is 0.98. And our confidence interval will be 67.02 to 68.98. We interpret this by saying we estimate with 95% confidence that the true population mean exam score for all statistics students is between 67.02 and 68.98. The 90% confidence interval is 67.18 to 68.82. The 95% confidence interval is 67.02 to 68.98. To be more confident that the confidence interval actually does contain the true value of the population mean for all statistics exam scores, the confidence interval necessarily needs to be wider. So our summary of this is the effect of changing the confidence level. Increasing the confidence level, going from 90 to 95%, for instance, increases the error bound, making the confidence interval wider. Decreasing the confidence level decreases the error bound, making the confidence interval narrower. Here's another example. Suppose we change the statistics exam problem to see what happens to the error bound if we change the sample size. Leaving everything the same except the sample size when using the original 90% confidence level. What happens to the error bound and the confidence level interval if we increase the sample size and use n equals 100 instead of n equals 36? What happens if we decrease the sample size to n equals 25 instead of n equals 36? So, accomplishing both of these calculations rapidly, we can see that if we increase the sample size to 100, we decrease the error bound. So n equals 100 will give us an error bound of 0.4935, while decreasing the sample size to only 25 will increase the error bound to 0.987. Our summary here is the effect of changing the sample size. Increasing the sample size causes the error bound to decrease, making the confidence interval narrower. And this should make sense because we know if we take larger and larger samples, we get closer to what the population mean would be, and we get an increasingly narrow normal distribution for our distribution composed of sample means. Decreasing the sample size causes the error bound to increase, making the confidence interval wider.